Okay, let's get an XY coordinate system going for this one. Put y-axis right there, x-axis, and we got some charged particles here. Hundred of them. I don't think I'll put them all in there, but let's single one out. They've all got the same charge. Q equals 1.21 nanocoulombs, where nano means times 10 to the minus 9th. And what we're interested in is the effect of all these charged particles at position 0,5 centimeters. So let's call it right up there. No, empty point in space up there is 0,5 centimeters. And the thing is, each one of them is contributing to the electric field at that location. So for instance, this one right here at some distance, I call it R, from the point in question is creating an electric field up in this direction. I'll call this the nth particle right here. So I got 1, 2, 3, 4, n is equal to 4, and this will be E sub n due to it. It's directed exactly away from it. Now each one of these particles is creating an electric field in a different direction. We got to add them all together vectorially to get the total electric field. So the total electric field will be E is equal to the sum for n is equal to 1 to 100, where this R is actually, I'll call it R sub n. So think of this as a generic particle. It's any one of them, and its distance from point P, I'll call that point P where we're calculating the electric field, is R sub n. So we got some n is equal to 1 to 100 of E sub n, the vector. And they're all pointing in different directions, so it'll be I think it'll be easiest to work in Cartesian coordinates. Let's go ahead and express this as the same sum, n is equal to 1 to 100 of, I'll call this EX, the x component, EX sub n, the x component of the nth particle, times I plus EY, nth component, times J. So it's the sum of all this. So I got 100 terms in the sum, and it doesn't matter whether I sum up each pair and then I have 100 terms of the pairs, or I add them up, you know, these 100 terms and these 100 terms, and then add the two results together like vectors, and that's what I'm going to do. So in other words, I can distribute this summation sign, and I'll call it n is equal to 1, from n equals 1 to 100, EX NI plus n is equal to, from 1 to 100, EYN times J. And then the thing is, in this sum of 100 terms, every one of them has an I in it, so I can factor that out. And similarly for the J. So what I have to do to get E, what I can do is find the x component for each particle of the 100 particles, add all the x components together, and do the same thing for the y components separately, and then I'll have the answer for E. So we got to get the components of E. I want to get a general expression for the components of E sub n. So for the nth particle, the electric field. I'll draw a vector component diagram. Is E sub n, and I can look at that as being at some angle theta, which depends on which particle I'm dealing with, so I'll call it theta sub n. And here's my vector component diagram with Ex n, Ey n. So Ex n over En would be the cosine of theta sub n. Multiplying both sides by En, we've got Exn is equal to En times the cosine of theta sub n. And then Eyn over En would be the sine of theta sub n. Multiplying both sides by En gives Eyn is En times the sine of theta sub n. Okay, now this theta sub n, if I take it up to this diagram, it's this angle right here. That's theta sub n, but by inspection, that's the same thing as this one right here. Now this particle, or this empty point in space, point P, is up a distance y, which is equal to, given as 5 centimeters. So I'll call that 0.0500 meters. And the particle that we're dealing with is at a distance I'll call x sub n. So it depends on which particle you're dealing with. But for the nth particle, it's a distance x sub n. So this cosine of theta can be expressed as, here's theta, the cosine of theta is this over that. So the cosine of theta sub n is x sub n over r sub n, and the sine of theta sub n will be this distance y, which never changes. It doesn't matter which particle you deal with, so I'll just call it y without any subscript. Y over r sub n. So I can express this as Exn is equal to En times Xn over Rn and Eyn is equal to En times Yn over Rn, where Rn is not known in advance, but I can express it in terms of Xn and Y itself. Rn by Pythagorean's theorem is Xn squared plus Yn squared, square root. So Rn is the hypotenuse of this triangle, so its squared is going to be equal to this side squared plus this side squared, and I take the square root of both sides and got an expression for r sub n. Okay, we've done a bunch of vector geometry here, but E sub n itself, we need that. E sub n, from your formula sheet in general, E due to a point charge is kq over r squared. And in this case, the only thing that changes is I got r sub n. So I need this expression for the magnitude of the electric field due to an arbitrary charge particle at a distance x sub n. And if I plug that into these expressions with r sub n plugged in there, I've got E sub x, Exn, I call it Exn, or E sub xn, for any arbitrary n, and the same thing for y. So I think I'm ready to at least create a table for use on a spreadsheet. So say I use an index n, and these particles go from minus 100 centimeters up to a centimeter. So there's none at the origin. There's one there, and then they keep on. There's one every centimeter from there out to minus 100 centimeters. So I'm going to try starting with 1, and then 2, 3, etc., down to 100 for n. And then x sub n is going to be, alright, the first one's at 1 centimeter. I think I really only need the magnitude x sub n. I guess this distance is x sub n, because the actual value, the first coordinate of that point is minus a negative value, and I just want that distance. So see if there's any place else. Here it doesn't matter because it's getting squared. So x sub n, the value of it will be this value times, I'm going to try n times 0.01 meters. And I don't really want a dot in there. Okay. I think I'll call that delta x. Some fixed value, so I can write this as n times delta x, because that's the spacing between them. So delta x is a good name for the spacing between them. And I think I can just copy that down. Quick check. 2 times delta x would make the x sub n, the magnitude of it, 2 centimeters. And that's exactly what I want. And then 3 centimeters, etc. Okay. So I'm going to need r sub n. And to get that, I'll need y, which is 0.05 meters. So r sub n is just the square root of x sub n. Think of it as magnitude squared, if you wish, plus the y squared. It doesn't matter which one I'm dealing with. That same expression is going to apply. Then what else do I need? I'm summing up these, so I'm going to go ahead and I think I'm ready for an expression for that. Well, let's get E sub n first. And that's K plus 9 Newton meter squared per Coulomb squared. So that's K Q over R sub n squared. And the value just depends on what R sub n is. KQ over R squared, essentially straight from the formula sheet. Okay, then EX sub n is En times X sub n over R sub n. And I just want the magnitude there. I think I was looking to see if there was one other place where that existed. And there it is, the X sub n itself. So for figuring out what the cosine of this angle was, I was just treating that as a distance. I wasn't using the abscissa of this point. Okay. And EYN is equal to EN times Y over R sub n. Okay, I think what I'll do then is get a table and a spreadsheet that's going to have 100 values of EXN, 100 values of EYN. I just have to add these up, and I'll have the X component of E. It's this piece. You know, I can interpret this as EX total, the total EX component times I plus total Y component times J. I mean, you can always write E that way. It's X component times I plus Y component times J, unless it's not. If it's in the XY plane, you can always write it like that. Otherwise, you get one more term with a K. But you know, by inspection, this is the E sub X and this is the E sub Y. So I think we're ready to go ahead and put that in a spreadsheet. Just go ahead and try copying those things in there. So I'm going to go all the way down to here. Call that E sub X. No, that was N. I'll put the titles in there. N, X sub N, R sub N, if I remember correctly. Then E sub N, EX sub N, I call it. E sub X N or ENX, doesn't really matter what order you use, but EYN. Let me check to see if those were the titles I had there. Yeah, it looks good. And then this is just N delta X. I need some numbers up here. We got delta X, Y, and K. Just call that DX, Y, and K. And this was, the particles were all 1 centimeter apart, so that's 0.01 meters. The position of the point where we were supposed to be finding the electric field is up at 5 centimeters, 0.5 centimeters, so that's that. And then this from the formula sheet, 8.99 times 10 to the, well, lowercase e takes care of the times 10 to the, and it's 9, and Newton meter squared per Coulomb squared. So this, I said, we'll have it go 0, 1, I'll go equals the previous value plus 1. And then the X sub N, ooh, I didn't want a 0 there. It's going to start that with a 1. The X sub N is equal to this times the delta X, which is at $A, $1 times $A, $1, using the dollars for absolute addressing, so when I copy it down, that part doesn't change, but this part, the reference to this guy next to it does. Okay, then this is supposed to be equal to square root of the thing I got next to it, squared, plus the Y, which is, I'll call it $A, $2, squared. Close parentheses. And I think I got it right there. This was really supposed to be absolute value of X sub N, because these particles are all to the left of the origin. And then this is equal to K times Q. I don't have a Q in there yet, so I'll put that right there. Slash R sub N squared. Okay, I need to put Q in. Call that Q. See what Q is. They did all have the same charge. 1.21 times 10 to the minus 9th coulombs equals 1.21 E minus 9, where the E means times 10 to the... Alright, that changed that. This, I think, I'll go equals the K, $A$3, times $3, KQ, so times, then I went $A$4, slash R to the 2. Not sure you use the dollars on these guys. So it's A3 should have been $A$3, $3, and then A4 should have been $A$4. And then C11 really was supposed to be C11 squared. Okay. This has got nonsense in there because I gotta look back here. EXN is supposed to be EN times X magnitude over R. So equals EN times X magnitude slash R. Okay. EY, EN times Y over RN equals E magnitude times Y, which is this thing, but I want an absolute addressing, $A$2, slash R sub n. Alright, I think that should do it. Let's try copying this down. Make 100 copies of it. Okay. Now what we're supposed to do is add these all up. So, put total. And this is equal to sum, this column, E, it went from 11 to 110. E11 colon means to E110. Let's make sure I got the whole thing selected. Yep. And hit return. And copy this over to here. And that should actually do it. So let's copy these values into the answer. 2.06 times 10 to the 4th. So using spreadsheet, find E equals 2.06 times 10 to the 4th newtons per coulomb, I, because that was the x component, plus 1.96 times 10 to the 4th. Newtons per coulomb times J. And that's my answer. To part A. And then, well, if we put a particle of charge 2.46, that was all part A, at that location, it's just going to experience a force that's its charge. I'll call that Q sub P. It's the charge that we're putting right there, times the electric field, the total electric field at that location. So part B, 2.46 picocoulombs, see if we can remember that. So for part B, I can just say F is equal to Q of that particular point times E total, which is, and no, I don't remember it, something times 10 to the minus 12, 2.46. Because pica means times 10 to the minus 12, and it was given as 2.46 picocoulombs. And then times this expression, 2.06 times 10 to the 4th newtons per coulomb times I, plus 1.96 times 10 to the 4th newtons per coulomb times J. And 2.46 times 10 to the minus 12. I've got this out, so I might as well use it. So this would be, I'll call this the force. And it's going to be equal to this times 2.46 E minus 12. And I can copy this one over to there. Verify it's F112, which is this thing. Actually, if I click on it, it highlights it. Times the 2.46 times 10 to the minus 12. Okay, so I'm getting 5.07 times 10 to the minus 8th plus, for the x component, 4.81. And the coulombs cancel, so I do have newtons times I. 4.81 times 10 to the minus 8th. Did I get those right? .07 and 4.81 times 10 to the minus 8th, and this is times J, so that would be the force, and that's the answer to part B, and that wraps up the